I'm Dr. Jason Furtado, assistant professor in the University of Oklahoma's School of Meteorology. I study large-scale patterns of atmospheric and oceanic climate variability, and today I'll be discussing how scientists represent variability and uncertainty in models of our climate system. Simulations of future climate change are done with many different types of climate models that can have many different configurations. They can have different resolutions, different parameterization schemes, and of course, their own model biases and errors. There are also multiple experiments run with each model to simulate past and future climates. The result is volumes of data resulting in many different and oftentimes diverging solutions of what future climate change will entail. We need to understand what the numerous model experiments mean and what sources of uncertainty are present in these model runs. One way to evaluate future uncertainty in our climate system is to conduct experiments known as climate change scenarios. These scenarios are run with each model to simulate past, present, and future climates using specific trajectories or pathways of how the environment, greenhouse gases, and aerosols change over time. In particular, future climate change scenarios from the Intergovernmental Panel on Climate Change's Fifth Assessment Report are called Representative Concentration Pathways, or RCPs. These scenarios are specifically named for the amount of radiative energy in watts per meter squared added to the Earth's climate system by the end of the 21st century. For example, the RCP 2.6 scenario means that the climate system gains a total of 2.6 watts per meter squared by 2100. While the RCP 8.5 scenario means a gain of 8.5 watts per meter squared. For everyday purposes, using radiative energy values for naming climate scenarios may seem abstract. To put these values into perspective, the average energy input by the sun into our atmosphere is 78 watts per meter squared. We can also think of these RCPs in terms of greenhouse gas emissions. For example, the RCP 2.6 scenario represents greenhouse gas emissions peaking in about 2020 and then declining thereafter, while the RCP 8.5 scenario represents continuously increasing greenhouse gas emissions throughout the 21st century. Comparing and contrasting the different RCPs allows us to evaluate the consequences of implementing various climate, social, and economic policies that affect greenhouse gas emissions. Unfortunately, without time travel into the future, we really don't know how well any particular RCP represents how the world will develop economically and socially in the future. The task of quantifying future climate change can be quite daunting when you consider the large number of climate models. The climate science community has settled on global surface air temperature as the metric of choice for evaluating future climate change. In particular, climate scientists define equilibrium climate sensitivity as how much the global surface temperature changes when carbon dioxide concentrations are doubled relative to the recent past. This climate sensitivity informs us what magnitude of radiative forcing is needed to significantly change the climate system. The equilibrium climate sensitivity from the over 30 climate models used for the Fifth Assessment Report varies from approximately 1.5 to 4.5 degrees Celsius. That is, a doubling of CO2 from pre-industrial levels are projected to cause a 1.5 to 4.5 degrees Celsius increase in our average global surface temperature. Along with equilibrium climate sensitivity, climate scientists also look to models for evidence of times whereby a small change in radiative forcing can create a large or sometimes irreversible change in the Earth's climate system. These critical thresholds are known as tipping points. There are many potential tipping points in the Earth's climate system, including the deforestation of the Amazonian rainforest, methane release from melting permafrost, or the melting of the Greenland or Antarctica ice sheets. Once these tipping points are passed, our climate system will reach a completely different state. If we look at the future projections of high-latitude land and sea ice, some models project rapid depletions in the next 100 to 200 years and tip past an irreversible point quite quickly. Other models show a more gradual decline and never reach that tipping point before the 100-year model run ends. As such, there is some uncertainty on what a future warmer Earth will look like. But why do the models vary so much in their projections for the same climate change scenario? Well, there's multiple reasons and sources of uncertainty for model simulations of future climate change. There are sources of uncertainty from model configurations, such as how models are designed and tuned to simulate cloud processes, turbulence, or ocean circulations. Some differences come about because different models are run with different spatial resolutions. These type of uncertainties are systematic errors or biases and will vary from model to model. Second, some physical processes in our climate system are less known scientifically. For example, scientists are still unsure exactly how aerosols in the atmosphere or circulations deep in the ocean affect the climate system, mostly because of few observations of these processes. There are also some naturally occurring processes in the climate system where models are unable to fully simulate all the features that we observe in nature. One example is ENSO, or the El Niño Southern Oscillation, where some models aren't able to accurately represent the amplitude of sea surface temperature variations associated with this phenomenon. Moreover, these internal modes of variability are a natural part of the Earth's climate system, and they can amplify or mute the large greenhouse gas-driven signal for climate change at different times, yielding different climate change solutions. Climate models provide multiple solutions for a future warmer world based on the various climate scenarios. The common elements for evaluation from the models are the change in global surface temperature due to a doubling of CO2, and evaluating tipping points in the climate system from which a return to the present state may be difficult or impossible. Multiple solutions from the models also mean we have to contend with uncertainty in our projections for future climate change. But with the built-in uncertainty, climate scientists can compute confidence intervals for the most likely scenario. For example, we are 95% confident that a doubling of CO2 will result in a change in global surface temperature between 2 and 3.5 degrees Celsius. What this means is that scientists believe there is very little chance that surface air temperatures will warm less than 2 degrees Celsius or be more than 3.5 degrees Celsius above present levels. These constraints can be very useful for decision makers, as they offer us a smaller range over which policy and planning decisions can be designed. In the end, even with various uncertainties in our projections, there are many aspects of climate change that scientists are confident about, and we will highlight these throughout our other videos.